Welcome back to another lecture. It's always good to see you. And this lecture, we're going to slowly start talking about organic chemistry. So whatever we covered until now was introduction from general chemistry 1 and 2. And in this chapter, we're going to this lecture, we're going to start learning how to draw a molecule in organic chemistry. The second lecture also will be general chemistry, and it will be talking about pKa and how to figure whether reaction is going to move forward or not. Okay, so in here, you've been given a Lewis structure of a molecule is an alcohol. How do I know it's alcohol? Because, forgive me, because we have OH attached to a carbon, and OH represent alcoholic group. So the OH is sitting on the second carbon. I can write it as a kind of like a condensed formula. When I say condensed formula, just simply, I don't show, like the H bond attached to carbon, the H bond for hydrogens that they're attached to carbon is because it will be easier actually to write it. So I started from entire of this space. I move to smaller one now, okay? And I can keep condensing the formula and I can write it now, okay? And I kept the functional group alone, but then I wrote the three carbons that attach to each other. And at the end, I can write the molecular formula. Molecular formula tells me almost nothing other than, yeah, we have three carbons there, 8 hydrogen and 1 oxygen. How they are connected to each other, no clue, okay? So now let's zoom on, for example, the OH group by itself. OH, it can be attached to the second carbon, okay, first carbon, or maybe it's a bridge between two carbons. So the first and second one, there are alcohol. Well, the last one is ether, okay? And here you have hydrogen bonding, okay, hydrogen bonding as well. And the last one is protic, doesn't have any hydrogen bonding, but it's polar. Okay, so mu is bigger than 0. That means this molecule will be polar, but it doesn't have hydrogen bonding. And the strongest force, it will be dipole-dipole, while the first and second strongest force, it will be hydrogen bonding. Of course, you have dipole-dipole and dispersion forces as well. Okay, so as I said, I'm gonna try to jump and show you how to draw organic molecule. So we're gonna use a zigzag model or a system to present any like any molecule, and the hydrogen atoms that they are attached to carbon for clarity or for easiness, and then for like to be easy. And like we ignore it, except when hydrogen atom is attached to heteroatom. And what do I do? What do I mean by heteroatom? Nitrogen, oxygen, or say like fluorine atom. Like you need to show if there is a hydrogen atom attached to them, you have to show them. Okay. So we're going to use the zigzag model for any carbon that has hybridization of sp3, okay, or sp2. Okay, so sp3 or sp2, any carbon here, okay, and it have sp3 hybridization. Okay, you can use this model for sp2 as well. So those two carbons, they have sp2 hybridization, but the terminals are sp3. Okay. And if it's sp1, okay, if it's sp1, because the bond angle is supposed to be 180, okay, you can use the zigzag model. Okay. Now, why do we use zigzag model? A zigzag model is trying to tell you that the theta or the bond angle for a carbon that it has tetrahedral geometry, okay, is 109, okay, around 109. Still, you can use it when it's sp2. Okay, it's not perfect, but it's fine. Okay, you can use it like for it, and still it will be good enough. But when it comes to sp hybridization, you have to draw it as linear. Okay, so we're going to start from here. we have 1, 2, 3, 4 carbons. So I'm going to say 2 carbon, and then I go down 3 carbons, and that's 4 carbon. Okay, the terminal carbon represent CH3. Okay, anyone in the middle here, it will represent carbon with 2 hydrogens. So, okay, let's write them more like in depth. Okay, so the molecule that we have is this. We have CH3, CH2, and then CH2, next CH3. Okay, so I have 4 carbons, and I start from here. I go 2, 3, 4. Okay, and this one represent, okay, terminal represent CH3, and that one also CH3. Okay, and any carbon in the middle. Okay, so let's highlight them. That carbon or that one, there will be, okay, there will be carbon atoms that they are attached to 2 hydrogen atoms. Same thing here. You have a carbon atom that attached to 2 hydrogen atoms. Okay, each carbon, it will have technically 3 bonds, 4 sigma bonds, so it will be tetrahedral. Okay, the bond angle, it will be 109.5. Okay, 109.5. Okay, again, each carbon, it has a 3 sigma, so the hybridization for any carbon is going to be sp3. Okay, cool. Now, when you're drawing them, okay, you try to respect the theta based on the hybridization. Okay, based on the hybridization. Okay, if it's a sp3, then try to keep it like 109. If it's sp2, you will try to keep it in around 120. If it's sp, then go with linear geometry. Okay, so for example, okay, if you have carbon, okay, attached to oxygen, okay, and that carbon is going to have 3 hydrogens. Okay, and again, I said whenever you have heteroatom, you need to show the hydrogen that attached to it. So here you go. Okay, that oxygen is not octet, so you need to add 2 lone pairs to it. Okay, so whenever you're trying to draw the molecule, you will draw it in a way, okay, in a way that like the bond angle is something around 109. Okay, 109. Why? Because here oxygen, it has sp3 hybridization, and same thing here, sp3 hybridization, forgive me. Okay, but how about this? Okay, compare it with this. Carbon that attached to oxygen, and the oxygen, it has 2 lone pairs. So the hybridization in this case is sp2. Okay, now what's going to be the bond angle between oxygen and carbon in any atom that attached to carbon? Any atom that attached to carbon. Okay, it doesn't matter what's that atom. It can be carbon, another carbon, or nitrogen, or whatever. Okay, say for example, we have here a hydrogen, and this one we have CH3. Okay, in that case, I'm going to say the hybridization for carbon, because it's is sp2, I expect this bond angle to be 120. And same thing here, I expect it to be 120 as well. Okay, why? Because carbon and oxygen both are both are coming with sp2 hybridization. Okay, so if you ask about this bond angle, that bond angle also is going to be 120. So this is the correct way to represent this molecule. It's not going to be correct to like to put oxygen between hydrogen and carbon. So let's say, okay, this is the correct version of it's not gonna be good presentation to put carbon there, hydrogen here, and then you draw oxygen somewhere there. Okay, why? Because whenever you're drawing the Lewis structure of any molecule, you try to maximize the bond angle. And in this case, you left entire of this space unused. Okay, that space completely left unused. Okay, well, you made the bond angle here. You drop the bond angle to something around 60. And same thing here, around 60. Okay, well, carbon, it has sp2 hybridization, so expected theta should be 120, and it's not. And that's the reason we say you need to follow the hybridization. You need to respect the bond angle based on the hybridization and also the lone pairs that you are dealing with. Okay. Next thing is, doesn't matter where, for example, I put the the bond, whether it's pointing up, down, and what I mean. So, for example, we have 1, 2, 3, 4, 5, 6 carbon. Okay, 6 carbon here. So I go 1, 2, 3, 4, 5, 6 carbons. Okay, or you can say this. Look, you can say this one is 4, and here 5, and call this one 6. Okay, so have a backbone that it has 5 carbon and one branch on third carbon. So total we have 6 carbon. Okay. So I go 1, 2, 3, 4. Okay, 5. And okay, how about this? So 1, 2, and here 3, 4, and this one is 5. Okay. Can I put number 6 somewhere here? That's fine. Okay, that's completely fine. Okay, and how about this? Can I draw it this way? Okay, let's say, can I draw it, for example? Okay, and then, okay, say, you have that one. Okay, give me. Okay, so I go 1, 2, 3, and next, let's say, you're gonna put this one down here. Okay, and make it 4, 5. Okay, that's another one. Okay, it's possible. Okay, or you can actually change direction on number 5 and drive this way. Okay. Okay, draw this one. Okay. You're going to remove that number 5 and draw it in this direction. That's completely fine. Okay. And that's going to be number 5. Okay. Why I keep saying this is completely fine? Because I'm trying to respect, like the bond angle. I'm trying to keep it around, 190, 109. Okay. And all of them are the same structures. Okay. And there's nothing wrong with any of them. Okay. Next. Okay, we said we try to remove any hydrogen that is sitting on carbon. So we don't show that one. Okay. But if you are dealing with heteroatom, what do I mean by heteroatom? Like atom like say nitrogen, okay, oxygen, sulfur, okay, phosphorus. Okay. You need to show any hydrogen that attached to that. Okay, because we want to know whether there is a hydrogen there or not. Why? Because if there is a hydrogen, okay, the physical and chemical properties of that object, that chemical component will be different. Okay. Yes, I know how to make it active, but first thing I need to know, do we have hydrogen sitting on it? If we have hydrogen sitting on it, I'm going to look to the rest of, the sigma bonds that attach to that heteroatom, and I try to give it some lone pair until I make it active. Okay. So when it comes to heteroatoms, you need to show like the hydrogen atoms that attach to them. Okay, you cannot ignore that part. Okay. No, like I don't know what happened with my PowerPoint. I'm gonna rerun it again. Okay. So when it comes to heteroatom, we need to show the hydrogen atoms that they attach hydrogen atom that attach to them. Okay, let's start with this. Okay. example that I'm going to go after it will be first oxygen, and then we're going to switch to nitrogen. Okay, so let's say we have an oxygen, okay, attached to one carbon, okay, and there is hydrogen attached to it. So this molecule is equal to carbon with 3 hydrogens, and then oxygen and oxygen attached to hydrogen. Okay, clearly oxygen is not acted. So what do I need to do with it? Okay, I'm going to say, let's draw a circle around it. Okay, we're going to draw a circle around oxygen. Next, what do we do with it? We're going to add 2 lone pairs. Why 2 lone pairs? Because we want to make it acted. It has used to have 4 electrons, 1, 2. Okay, so put it this way. We had 2 electrons plus 2 sigma bond. That's 4. We are short by 4 electrons from 8, and that was the reason I gave it 2 lone pairs. Next, how about the formal charge? Okay, the formal charge for oxygen. Oxygen in group 6 minus, I see 6 electrons around it, so it will be 0. Okay, it will be 0. Next, what if there is no hydrogen attached to it? You will draw it like, let's say you drew it that way. Okay, you drew it that way. Okay, this is going to be equal to carbon attached to oxygen. Okay, what else? Okay, this one, it has 3 hydrogens. Okay, 3 hydrogen there, and oxygen. I need to make it octet. Let's draw a circle around oxygen. Okay, oxygen right now it has 1 plus 1 electron. 2 is missing 6 electrons. We're going to give it 6 electrons. So we go 1, 2, 3, 4, 5, 6. We gave it 3 lone pairs. Okay, let's find the formal charge. We go oxygen is a group 6. But I see 7 electrons around it, so oxygen is -1. Okay, but what will happen if we have 2 hydrogens there? Okay, so we go, okay, oxygen attached to 2 hydrogens. Okay, okay. This one representing carbon with 3 hydrogens that attach to oxygen, and oxygen happened that have has 2 hydrogens attached to it. Okay, let's check whether it's octet or not. Okay, so what do I see here? I see 3 plus 3, that's 6. I need 2 more electrons to make it octet, and I'm gonna put 2 electrons there. So there is a lone pair. Okay, there is a lone pair in oxygen. Okay, let's draw circle around it again, and we need to find the formal charge. Oxygen in group 6. How many electrons do I see there? I see 5 of them. So oxygen is a +1. Okay, so it depends how many hydrogens sitting on oxygen. The formal charge is changing. If you have 1, it will be 0. You have 2 of them, it will be +1. If you don't have any hydrogen attached to it, while oxygen is attached to 1 carbon through a single bond. Okay, single bond, not double bond, single bond. In that case, the formal charge, it will be 0. Okay, it will be 0. What if I draw oxygen here? If I draw it this way, okay, let me move this one, all of this bit up. Okay. How about this? What if I go, let's say, carbon, go. Oh, okay. Your carbon is not octet. Oxygen clearly is not octet. So what do I need to do with it? Okay. Okay. Means carbon supposed to have 2 hydrogens. So as you see, we did not show the 2 hydrogens on carbon. Okay, how about oxygen? Oxygen attached to carbon through a double bond. Okay, how do I make oxygen octet? Okay, let's draw a circle around oxygen. Same thing here. Okay. For oxygen, we're going to add 2 lone pairs. Okay, oxygen is going to be a group 6 minus. Okay, how many electrons do I see around it? I see 6 of them. So it will be 0. Okay. So as you see, when it comes to heteroatom, again, heteroatoms, nitrogen, oxygen, say phosphorus, sulfur. Okay. When it comes to heteroatom, okay, from day one, from the beginning, we know exactly how many hydrogens are there. They need to show it. You need to show it. Okay. Those, they were there from day one, from the beginning. I did not manipulate those. Okay. In order to make the element acted, we add lone pair to it. Okay. We add lone pair to it to make it acted. But how about carbon? How do we make carbon acted? We add hydrogen to it. Okay. Listen carefully. For heteroatoms, we add lone pairs until we make them acted. For carbon, we will keep adding hydrogen atoms until we reach acted. Okay, let's repeat this story for nitrogen. Okay, so say you have carbon attached to nitrogen, and nitrogen has 2 hydrogens attached to it. Okay, carbon attached to nitrogen. Okay, and nitrogen has, okay, we can start with, forgive me, we can start with, for example, with 1. Okay. That's maybe it's not going to be a really good example. So let's skip it. Okay, 2. And then we go carbon attached to nitrogen. Okay, we're going to add 3 of them. Okay. This one is equal to a carbon with 3 hydrogens. So I'm going to say H3 technically. And there is a nitrogen, and nitrogen, it has 2 hydrogens attached to it. Okay. Here, again, you have H3, C, and then nitrogen attached to 3 hydrogens. Okay. How about the formal charges? Okay, let's check carbon. Sorry, nitrogen. So we're going to check nitrogen in all structures. Okay. Nitrogen is not acted. It's missing 2 electrons to be acted. So I'm going to add a lone pair. Okay. Nitrogen is a group 5. But I see 5, yeah, and then also I see 5 electrons around it, so it will be 0. Formal charge is 0. Okay, next one. Nitrogen, okay, 1, 2, 3, 4, okay, 4, and made 4 sigma bonds, so nitrogen is acted. So I'm going to say nitrogen is a group 5, but I see only 4 electrons around it, so nitrogen will be +1. Okay, so from 0, now we turn it to +1. Okay, how about this? Okay. Carbon attached to nitrogen, we have only 1 hydrogen. Okay, we have only 1 hydrogen. Okay, in that case, I'm going to say this is equal to, you have H3, carbon, and then we have nitrogen. Okay, and we have a hydrogen here. Okay, let's draw circle around nitrogen. We're going to keep adding lone pair until we make it acted. I need 4 electrons, 4 more electrons to make nitrogen acted. So what's going to be the formal charge for nitrogen? Nitrogen is a group 5. Okay, how many electrons do I see around it? I see 6 electrons around it. So the charge will be -1. Okay, the charge will be -1. And last one. Okay, last one. How about this? Okay, how about this one? Okay, and okay, in this case, I'm going to say carbon is not acted. Okay, okay, so let's add 1 hydrogen to carbon. Okay, how about nitrogen? Okay, nitrogen. Okay, we're missing 2 electrons to be acted. So we're going to add 2 electrons on nitrogen. And here you go. It will be acted. And how about the formal charge for it? The formal charge for it. Okay, nitrogen is a group 5. I see 5 electrons around it. That's gonna be 0. Okay, that's 0. So how did we get, to 0 formal charge? We made triple bonds with nitrogen. Okay, so 3 bonds with nitrogen made it. Okay, made it, technically made the formal charge 0. So we got 3 bonds plus 1 lone pair. 1 lone pair. Okay, let's go back. We had one structure that has also had the formal charge equal to 0. And here we have 3 bonds and 1 lone pair. Okay, so if nitrogen manage to make, 3 bonds and 1 lone pair, the bond angle, the formal charge is going to be equal to 0 for it. Okay, I believe I'm gonna, like I cover, both oxygen and nitrogen. So I'm gonna stop here. And the next lecture, I will try to go through carbocation and carbanion. Thank you very much. And as always, I will see you soon. Thank you.